Okay. Hello. Hello, this is Advanced Computer Vision. We are Group 7, which consists of Serenity, Andrew, Bradley, Salim, and I, Daniel. Today we would like to present grounding DINO, marrying DINO with grounding pre-train for open set object detection. Here we have the authors of this paper, and this paper has 420 citations. Okay. Here we have the outline of our presentation, which first we're going to talk about the background, which gives insight of open and closed set detection. Then we're going to talk about grounding DINO and its related work, followed by its architecture, experiments, and applications. Okay. So some background before we dive deeper into the model is that from previous papers is that traditional object detection models are trained on a fixed set of classes, which can lead to certain limitations for unseen data. Now, trying to add new classes can be expensive and time-consuming, which can lead to models not being flexible. Therefore, grounding DINO focuses on open-set object detection, which allows the model to identify objects of unseen classes. Next, I'm going to show you an example and explanation of what closed and open set detection is. First, we have closed set detection, and closed set detection focuses on detecting objects of predefined classes. So here's an example of using closed set detection with COCO pre-trained categories. On this first example, we have a three lions lying on a bench, where we have the category bench, and I know it's hard to see, but around the bench area, there is a bounding box for that category. And an example below, we have a World Cup final of people celebrating. So for the category person, we can see multiple bounding boxes around the that category or around people. So this is what we know from the standard object detection. Now, if we move to open set detection, which detects objects that were not present in the training data. So by using the same example from previously, a human can now input categories that again were not present on the training data. So now we have the category ear, lion, and bench, and we can see a bounding box around those areas. From example, the ears, the lions, of course, and the bench again. And on the example below, now we have the category World Cup, which we can see a bounding box around the World Cup area. So this can be seen as a zero-shot transfer to novel categories. Okay, so now we move to grounding DINO. And a brief introduction of the model is that grounding DINO is a strong open set object detector which combines transformer-based detector DINO with grounding pre-train. And by being an open set object detector, it introduces language for unseen object generalization and detects arbitrary objects with human input that, for example, can be categories such as the previously shown, or referring expressions which we are going to show later on. Here, I would like to emphasize that the key point for having an open set detection is adding or introducing language for unseen data generalization. And of course, we add this with a closed set detection. And by combining these two, as a result, we get a open set detection. One important key of this is that the stronger the closed set detector is, the better results you're going to get with the open set detection. Okay. Now, by using the transformer-based detector DINO, which not only achieves a state-of-the-art in object detection, but it also lets integrate multi-level text information. And by adding this with the grounding pre-train, we obtain the model grounding DINO. This is just to avoid any confusion when we're referring to DINO DTAR with improved denoising anchor boxes for end-to-end object detection, and not DINO, emerging properties in self-supervised vision transformers. Okay. So now we have the related work for detection transformers. So grounding DINO is built upon DTAR-like model DINO, which is an end-to-end transformer-based detector and leverage the strengths of the original DTAR model. Of course, there are other models that are built upon DTAR, such as DAP-DTAR, which introduces anchor boxes for more accurate prediction, and DN-DTAR, which proposes a denoising approach to stabilize bipartite matching. Of course, however, these detectors mainly focus on closed detection, which are limited by the predefined categories. Okay. So this is related work for DTAR. DTAR uses a convolutional neural network or CNN backbone to learn the 2D representations of an image input, then is flattened and supplemented with positional encoding and passes to the transformer encoder. Then we get to the transformer decoder, and the transformer decoder take it as input a small fixed number of learned positional embeddings, which they call object queries. And from this, we get an output embeddings from the decoder passed to a shared feed-forward network or FNN, which we can get a predict detection, which can be class and bounding box or no object. Okay. So if we move forward, this is the framework proposed for DINO model, which follows the DTAR architecture. So given an image, we extract the multi-scale features with backbone, like ResNet, then is fed into the transformer encoder with corresponding positional embeddings. And after enhancement with the encoder layers, a new mix of query selection strategies to initialize anchor as positional queries for the decoders is used, as over here. Now with the initialization of the anchors and the learned content queries, they use the formable attention to combine the features of the encoder outputs and update the queries layer by layer. The final outputs are formed with refined anchor boxes and classification results predicted by the refined content features. Okay. Now I'm going to talk about the related work for open-SEP object detection. So most existing open-SEP detectors are created by extending or adapting closed-set detectors for open-SEP situations using language data. Generally, a closed-set detector has three main modules: a backbone for feature extraction, a neck for feature enhancement, and a head for refinement or box prediction. So this figure represents the existing approaches to extending closed-set detectors to open-set scenarios. So what is now highlighted in red represents the three main modules I recently talked about. And an important part of this is that some closed-set detectors can have only partial phases of these sections. So again, here we have the backbone, which can be ResNet or swing transformer. From this, we get the image features, and then we pass it to the neck, where on the neck we have a dynamic head or die head, and a dynamic head unified subject detection head with attentions, or we have your typical encoder. So from this one, we get the refined image features, the query initializations, and finally we get to the head, where we have a radio head or decoder, and from this we get the output regions. So a closed-set detector can be generalized to novel objects by learning the language regions embeddings. But the key to do this is using contrastive flows between the regions and language features at the neck and or the head outputs, as we can see in this figure. So, yeah. So language features can fuse at different phases, such as phase A, which is the neck, so this section, where for example, the click model performs early fusion, and then we have phase B, query initialization, so in this section, where the model OB-DTAR uses language-aware queries as head inputs, and finally, we have phase C, which is the head. So in existing open set detectors, multimodal feature fusion is done in partial phases, and referent expression comprehension, or REC, is overlooked during the evaluation. Now Serenity is going to continue with the model architecture.
Okay, so I'm continuing with the model architecture. So grounding DINO is a dual encoder, single decoder architecture. It has 5 main key components: image backbone, text backbone, feature enhancer, language guided query selection, and cross modality decoder. So this is a high level diagram of the architecture. So initially they send an image and a text pair, and we take an image and a text pair and pass it to the encoders. So in this case, the image backbone is swing transformer and text backbone is BERT. So they get the image features and text features respectively. Then it is passed to a feature enhancer to further improve the features. And next stage is they pass those features to language guided query selection. So here basically they select the image features which are more relevant to the input text. And the output is cross-modality queries from that layer. And finally, it is passed to a cross-modality decoder. So here they perform cross-attention with those cross-modality queries and image text features to get the final bounding box queries. So at the end, they perform loss to get the final output. So here, basically, they perform contrastive loss for classification and localization loss for bounding boxes. So as you can see here, they fuse language in 3 main phases, which is feature enhancer, language guided query selection, and cross-modality decoder. So let's go into these components in more detail. So the first component is feature enhancer. So first, it takes those text and image features from the encoder, and it performs self-attention. And next, they perform image to text cross attention using queries from image features and text from the using key and value from the text features. Next, they do the opposite, where they perform text to image cross attention using queries from text features and key and value from image features. Finally, those features go through a feed-forward network and get the updated image and text features. And the next stage is language-guided query selection. So here what they do is basically use the text input and select the most relevant image features as object queries for the cross-modality decoder. So this is the third stage, which is cross-modality decoder. Here you take the cross-modality queries, which were sent from the previous stage, and you perform self-attention on it. And then you use those queries and key and value from image features to perform cross-attention. And again, you perform cross-attention with text features and pass it to a feed-forward network and get the updated queries for the detection. And the next is a sub-sentence level text feature. So here we discuss about how the model will represent the text prompt. And there are 2 existing approaches. The first approach is sentence level representation. So here it treats the entire sentence as a single unit. As you can see in the image, cat is treated as a single unit. Baseball glove is treated as a single unit. And here in the if the sentence has more than one phrase, it extracts only the phrases and ignore rest of the words. So in this case, they have considered cat and table and ignored this part of the sentence. Also, there is no interaction between these features. So there are two main drawbacks in these limitations in this method. One is it removes the influence between words and also the fine-grained information in the sentence. The next approach is word-level representation. So here they treat each word separately, unlike the previous method. So as you can see, cat is a single feature, baseball, a single feature, and glove, and so on. So also they consider the interaction between each and every feature here. There's a limitation. It introduces unnecessary dependencies among those categories. So as a solution, grounding DINO introduces sub-sentence level representation. So here they maintains per word features for fine-grained understanding. So also it introduces attention mask to block the attention among unrelated words. So as you can see in the image, so there is no relation between cat and baseball. So the loss functions, so there are two main parts in the loss they have used. First one is contrastive loss. So basically they're trying to get the contrastive loss between text features and bounding boxes. So in the image, you can see it's a table here. So it's positive over here and cat, and it's positive over here. So they're trying to bring the similar text and image features together here. The next loss is the localization loss, what they use similar to DETR. Here they use the L1 loss and GIOU loss for bounding box localization. Now let's see a comparison between DINO and grounding DINO architectures. So this diagram shows the entire view of the grounding DINO model, and this extends details of cross-modality decoder and feature enhancer. So in blue color, they have highlighted the newly added features in the grounding DINO model, which is mainly the text features. So they have added this text backbone, and in the feature enhancer, they have done image and text process attention. And in the language guided query selection, they have added newly, and also they perform process attention again in cross-modality decoder here. And finally, they perform contrastive loss with text features. So that is a high-level idea between the grounding DINO and DINO models. So now Andrew will continue with the experiments. Thank you.
Thanks, Sarandi. So let me switch over my screen. So I'm going to start talk about the experiments for grounding DINO. And in these experiments, we compare grounding DINO against other open set.
Can you talk louder? We cannot hear you.
One moment. Do you hear me now?
Yes.
Okay. So in these experiments, we compare grounding DINO against other open set vocabulary detection models, such as.
Mic closer, we cannot hear you.
Yeah, just hold the mic.
How about now?
No,
Oh.
not much improvement.
Not much. Okay.
We can hear him.
Hi now,
Is this better?
We can hear you fine online.
could you talk something?
Hello? Do you hear me, Sweeta?
We can hear him online.
Yeah. Change to text. Could you continue talking?
Yes. Do you hear me now?
Let me try one more setting. You
Okay.
talking?
So in the experiments, we are going to compare. How's that now?
Okay, you can, yeah, you can do now. But keep the mic closer. It's very hard to hear.
Okay. So for grounding DINO, we have a couple experiments where we compare the model against other open set vocabulary detection models in 3 different settings. First, we evaluate the model in zero-shot transfer of settings, where in the first setting, we look at the COCO benchmark. In this benchmark, we compare grounding DINO variants, grounding DINO large and grounding DINO T against the GLIP large and GLIP T model, as well as DINO base and SWIN T forms and SWIN large. On the COCO benchmark, we see that this grounding DINO compares with both GLIP L and DINO L, but outperforms the model by 0.5 percentage point on the Object 365 pre-training data set. Additionally, the model actually sets a benchmark as we scale up the data and actually outperforms all the other open set vocabulary detection models when it comes to zero shot for COCO benchmark. The second setting that we evaluate is grounding DINO on the LVIS benchmark, where LVIS is used more so for the long-tailed vocabulary sets. So in this model, we see that grounding DINO outperforms GLIP. And in this scenario, we're only comparing grounding DINO against GLIP because there wasn't a similar evaluation for base DINO, but we can see that grounding DINO outperforms GLIP T by over a percentage point on the average precision metric. However, we do see that in the rare settings where we have objects that are not common, we actually have a dip in performance in comparison to GLIP-T. The authors believe that's due to a limitation with the number of queries in the language query design guided query selector portion of the architecture. The third setting that we evaluate grounding DINO on the zero shot benchmark is in the out in the wild object detection data set. This is a more challenging data set since there are more real world scenarios and more data sets. Grounding DINO in this data set is compared on 3 settings, where the first setting is in zero shot, then few shot, and then full shot. And what we see is that grounding DINO outperforms DINO base with a T scale model as comparison to the base DINO large. And additionally, the model starts to perform very well when we introduce the actual scene data set. So you can see that the model outperforms GLIP-T and base DINO. Next, we move to referring object detection sets, where we are using the rec task, which allows us to compare the model in a natural language setting where we want to find fine-grained features against the objects. So grounding DINO actually performs not that well when it comes to having unseen rec data sets, but when we introduce additional pre-training data, the model greatly outperforms GLIP by almost 40 percentage points on val for ref COCO and over about 33 percentage points for ref COCO plus. Then grounding DINO, it performs very well additionally when we scale up the data set. Then we're going to move on to the ablations. In this portion of the experiments, we want to evaluate the effectiveness of each fusion module for grounding DINO. So the authors show that each portion of grounding DINO actually contributes to its performance, with the encoder fusion being the most important fusion component of grounding DINO. And that each fusion portion of this architecture actually contributes the model's performance. Finally, we look at how we can transfer weights from base DINO over to grounding DINO. In fact, we would like to see how well we can use these pre-trained weights to then train the other components of grounding DINO that are not a part of DINO. And what we see is that there are similar performances between base DINO and grounding DINO when transferring those pre-trained weights from the DINO architecture, and that we actually see a greater convergence of the model for grounding DINO T when we use those pre-trained weights. So that wraps up the experiments, and I'll pass it over to Brad for the applications.
My screen visible?
Yes, it is, Brad.
So the main application that we're going to be discussing that is discussed in the paper for grounding DINO is marrying grounding DINO with stable diffusion as well as GLI gen to attempt to, use DINO to here with stable diffusion. It will you input two different things, a detection prompt and a generation prompt. The detection prompt is similar to prompts that you see earlier in this presentation for detection. As you can see here, the detection prompt given is Green Mountain, and it creates this bounding box around what it detects as the Green Mountain. And then the second input will be considered as the generation prompt, and it will then pass this image with the bounding box and create it as an in-paint section for stable diffusion, which will then be used to in-paint over the bounding box detected by DINO. And these are some example outputs that you get by trying to take the Green Mountain and change it into a red mountain. And then here, similar detection prompt is a running girl. You see that it puts a bounding box around the girl, and then the generation prompt is set to modify the background, and you can see how it changes the background and leaves really only the in-painted section unedited. A few more examples of how this is done is you can see this image from earlier in the presentation of the 3 lions. It specifically asks for the left lion. The left lion is detected by DINO. And then this detection area is passed to stable diffusion for in-painting and will then modify the detected object into a dog. Similar here, where it asks for the bottom man with his head up. It will detect this zone, create it as in-painting, and modify the background using stable diffusion. And next, they try to combine grounding DINO with GLI gen. Similar in concept to stable diffusion, except it also has the added bonus of having a phrase prompt. So rather than just having the detection and the generation, you can also use the phrase prompt to input phrases for each of the boxes. So essentially it allows you to take 2 different detections. You can see here a dog and a cat, and then using the phase prompt, you can change individually the 2 different detected sections standing alone by themselves. And you can see here, similar example, it detects the two different sketched individuals and replaces them individually with a woman and a man who are talking as given by the generation prompt. Some of the limitations for grounding DINO is that it lacks capability for segmentation tasks. The limited amount of training data restricts performance potential for the model. And then the future work that they spoke about was conducting larger scale training to enhance scalability, improve the training of grounding DINO using the pre-trained weights and models for the original DINO, and enhance their zero-shot performance for the rec tasks. In conclusion, basically what this all brings together is that it extends the original DINO model to open set object detection, introduces fusion approaches for cross-modality and information, and proposes subsentence level representation for leveraging that detection data, as you can see by the applications with stable diffusion. And it also extends the open set detection for rec tasks. Thank you, everybody.